So this is the final week of our course on implementation of quantum computing. So what we will try to do in this week is go back to the basic ideas that we started from and give you all the summary of the implementations and the aspects of the quantum computing that we have learnt as a part of this course. So, perhaps this week will have a little longish in terms of the number of lectures and the amount of material, just to make sure that we are able to cover most of the materials that we have presented in this course. Also, we will try to look at some of the difficulties that some of you had in your responses in the forum and other places. So, there may be places where I also refer to the areas of difficulty that you had while doing this course, so that we can sort of finish all the parts which were not possible to be addressed during the course. So, I have set it up in such a way so that we go from the point of the background where we started this course, which was classical computation, wherein we gave examples of how classical computer can be essentially looked at in terms of the Church-Turing Thesis, which essentially means that it is anything that can be done in a Turing machine. This definition coincides with our intuitive ideas of computation, addition, multiplication, binary logic, etc. So, in terms of a Turing machine, we have discussed it as a machine which has a way to read, write data on an infinite tape and have a control module which is in a finite state automation, so that it can achieve the computation on the input data to give rise to the result, which is the output. So, in this principle, problems which can be posed only in a way which can undergo specific answers are the ones which can be addressed. So, that is the part which we discussed in terms of the concept of computing. So, universal statements, for instance, are not information which can be used for doing computation, and so on and so forth. So, we had done quite a bit of discussion on this area of computation. Now, the other important part of the computation lies in the concept of complexity, which was also importantly addressed in this course, where we have discussed the levels of complexity that appears in computation. Some problems are more difficult than the others. Generally speaking, all the computable problems that are addressed through the Turing machines have polynomial hierarchy, and as such all Turing machine equivalent computers have identical hierarchy. So, there is this typical way of presenting how the computer complexity looks like. The part which is solved quite regularly by Turing machines or our computers are the ones which require polynomial time to solve, which is the complexity in terms of p, and then the ones which have difficulty starts from the parts which are non-determinate polynomials, and so there are two parts to it, one which is known as non-determinate polynomial which require times which are definitely exponential to solve, which are known as NP complete, whereas the others which are exponential requirement in time, but under certain conditions can be transformed into certain levels of polynomial times. So, those are the two different parts of the difficulty levels. So, it is either NP non-determinate polynomial or NP complete, which is the hardest part of the difficulty in terms of doing this work. So, this is how we had discussed in terms of classical computing. We also referred to the fact that some important problems do not have the known classical polynomial algorithm and or a known place in the hierarchy. So, in this picture of polynomial hierarchy, for instance, Factoring is a problem which works in exponential time. For instance, the best known algorithm to factor n digit number takes time which is about exponential n to the power 1/3. So those are the ones which go out of this polynomial hierarchy, and they are classically difficult problems to be done. There is also this problem of graph isomerism. Best known algorithm to compare two node graphs is also an exponential problem. Similarly, search problems can often run into regimes which are not quite in the polynomial regions, and they could be also non-determinate polynomial in some sense. In this case, we mentioned quantum systems can be of huge help to us. Quantum systems is a system of elementary particles like photons, electrons or nucleus governed by the laws of quantum mechanics. So we deviate from the concepts of classical nature that we were discussing when we discuss in terms of quantum mechanics. So in this regard of complexity, one of the concepts that we introduced was the idea of using quantum systems. When a system becomes small, such as a quantum system is a system of elementary particles such as photons, electrons or nucleus, which are governed by the laws of quantum mechanics, and therein the concepts of classical mechanics are not quite applicable, and thereby we can think of computations which are no longer in the classical domain that we were discussing until now. So the idea was to take advantage of it. So the parameters in this particular case for this system may include positions of particles, momentum, energy, spin, polarization. The quantum system can be characterized by its state that is responsible for the parameters. The state can change under external influence, which could be fields, laser impulses, etc. It could, and finally those are to be realized or found out the results in terms of the measurements. So these are the basic principles of the quantum system coming into the picture in place of the classical nature of objects that we just discussed. The distinction of quantum mechanics lies in certain points. For example, in terms of superposition, if a system can be in either of the two states simultaneously, it also can be in a superposition of them. This is distinct from what a classical nature of a system is supposed to be. Some parameters of elementary particles are discrete. For example, energy, spin, polarization of photons, and that is how they are quantum in nature. The changes in this particular case of quantum mechanics are all reversible. That is actually a very important parameter also, and a critical part of quantum mechanics lies in the fact that the parameters are undetermined before the measurements, and so this plays a very vital role in terms of the application of quantum mechanics into the classical areas that we are discussing. Another important aspect of quantum mechanics that is distinct from classical mechanics is that the original state is destroyed after the measurement. There is nothing which can be cloned, and so that comes under the no cloning theorem, which says it is impossible to create a copy of unknown state. And the point here is that once you make a state known, then it does not remain as quantum anyway, because it becomes classical. Finally, there is this concept of quantum entanglement and quantum teleportation. All of this has been a part of your course in great detail. We are here just revising and refreshing it in order to make sure that we are completing all the parts of the course that we have covered in this series of lectures that we have done. So one of the term which we introduced in this was the idea of a qubit, which is the quantum bit. So that is our unit of quantum operation. In general, one qubit simultaneously contains two classical bits, and that is one of the important aspects of quantum mechanics which is inbuilt into the system. Qubits can be viewed as a quantum state of one particle, photon or electron. Qubits can be modeled using polarization, spin or energy levels, all those which assume discrete values. Qubit can be measured. As a result of measurement, we get one classical bit, either 0 or 1. So, until the point of measurement, as has been correctly pointed out, quantum mechanics ensures the result or the information can be embedded in terms of qubit, which can contain both the classical information simultaneously. Therein comes the concept of quantum computer whenever we use quantum mechanics. Quantum computer uses properties of elementary particles that are predicted by quantum mechanics, and so that is how we arrived at this whole concept of quantum computer or quantum computing. Usual computers, as we have been showing in the very initial slides even today, the information is stored in terms of bits, whereas in quantum computers information is stored in terms of qubits, quantum bits. Theoretical part of quantum computing is developed substantially, as we have shown. However, practical implementation is still quite a big challenge, although we have discussed in this course some of the even commercial approaches of quantum computing. So, this point, the practical implementation point, though is still an issue, it is not really a difficulty which has not been overcome as of yet. There is a strong connection of quantum computers with probability. That is also another thing that we have discussed in length in this course. When the quantum computer gives you the result of computation, this result is correct with certain probability. Quantum algorithms are designed to shift the probability towards the correct result. That is one of the most important aspects of quantum algorithms. Running the same algorithm sufficiently many times gets the correct answer with high probability, assuming that we can verify whether the result is correct or not. The number of repetition is much smaller than for usual computers, and that is the power of quantum computer. So, here is a short history of quantum computing which we have discussed in this course earlier also. From about 1970 onwards, the beginning of quantum information theory started. In 1980, Yuri Manin first set forward the idea of quantum computations. Paul Benioff at about the same time discussed with Richard Feynman on the concept that as the computers become smaller, errors in computers become larger due to the probabilistic concept of quantum behavior, and the solutions would becoming more and more probabilistic. Feynman thought about the problem and he independently proposed the use of quantum computing to model quantum systems. Since quantum systems are the essential building block of nature, he thought that was one of the best ways of addressing quantum systems by building quantum computer rather than dreading the idea. He also described the theoretical model of a quantum computer based on this thought process. However, it was not until 1985 that the concept of how such a principle would become useful was given by the idea of David Deutsch, who described the first universal quantum computer. And then came the big breakthrough in 1994, where Peter Shor developed the first algorithm for quantum computer, which is the factorization into primes. Now, this was one of the most important developments perhaps in the area of quantum computing, which essentially made people realize that it could really have a huge impact because of the break of the RSA codes and other kinds of things. So, this was a very important development, and it took almost a decade to get there, because a lot of error solving and other kinds of problems were being worked on during this period of initial development of quantum computer. In 1996, Lovegrover developed an algorithm for searching in unsorted database, and this was also extremely important because turns out that for many problems it is known that the solution exists, but it is more of a searching of the solution which is the biggest step in computation. And therefore, getting an algorithm which would be able to search for a solution has a huge impact in this area. In 1998, the first quantum computer on 2 qubits based on NMR was built in MIT, Stanford and IBM. In the year 2000, quantum computer on 7 qubits based on NMR was built in Los Alamos. Another major development in the year 2001 was when the number 15 was possible to be factored on the 7 qubit computer by IBM, and this was achieved by Chuang and his group. In 2005 to 2006, experiments with photons, quantum dots, fullerenes and nanotubes as particle traps started becoming popular, which resulted and developed this field further to finally the first commercial computer, quantum computer, which came out in 2007, where D-Wave announced the creation of a computer on 16 qubits. So, looking a little bit into the basics here, a model of a qubit, as has been discussed several times, essentially can be represented by a vector with a ket representing vector having the states 0 and 1, such that the coefficients a0 and a1 can be complex numbers with only the constraint that their mod squares add up to 1. This state or the qubit psi ket is a superposition of the basis sets 0 and 1. The choice of the basis states is not unique, which means that several possibilities exist. The measurement of the wave function psi ket results in, say, the bit 0 with probability a0 mod squared and in bit 1 with probability a1 mod square. After the measurement, the qubit collapses into the basis state that corresponds to the result, and this particular part is essentially classical. So, the point of measurement brings back the classical information as we have been discussing. So, here is an example just to show that the coefficients basically give rise to the probability of the measure of individual states. So, this idea of using computation with qubits, how does it affect the concept of computer? So, in terms of classical computation, the data unit is, as mentioned, either 1 or 0. So, the valid states are either 0 or 1, and depending on how the switch is, whether it is pointing towards 0 or towards 1, we get the values as 0 or 1. In terms of quantum computer, however, the data unit, which is the qubit, has the valid state in the superposition of both 0 and 1, and at any point of time before measurement it can assume any of the values that are possible. In both cases, logical operations are to be performed. However, in classical computation, logical operations need not be reversible. So, for instance, NOT gate, where it is a one input and one output, it is a 1-bit process, is perfectly fine. However, it also admits 2 inputs and 1 output in terms of the AND gate. In terms of quantum computation, which is definitely going to be only unitary and reversible, the valid operations therefore involve, for example, in terms of 1 qubit, the Pauli matrices as we have discussed throughout this course, as well as the Hadamard operation, which basically produces an equal superposition of the states concerned. In 2 qubit case, there is this control NOT, which enables the switching of a bit based on the control. However, it is important that all the logic gates in terms of quantum computation be reversible. In case of classical computation, the measurement is deterministic. If the state is a 0, then the result of the measurement would be 0, whereas if the state is 1, then the result of the measurement will be 1. On the other hand, in quantum computer, the measurement is probabilistic or stochastic. As a result, we could land up having the measurement of either 0 or 1, as well as the case where both 0 and 1 occur with a 50-50 probability. So, these are the major distinctions which can be immediately looked at when we look at computation with qubits versus the computation with bits. When we are using several qubits, the subsystem of n qubits contain 2 to the power n classical bits or the basis states. So, here comes the exponential benefit in terms of the classical computing. The potential of quantum computer grows exponentially. We can measure individual qubits in the multi-qubit system. For example, in a 2 qubit system, we can measure the state of the first or the second qubit or both. The results of measurement are probabilistic, as we just showed. After the measurement, the system collapses in the corresponding state. So, here is how it looks like. We are, in terms of quantum computer, working in the Hilbert space. For a single qubit, we have already seen how it works. When we have 2 qubits, they work as tensor products, and so there is an exponential growth in the space. For any arbitrary state, for a single qubit, the coefficients are just the 2 coefficients of the 2 states. However, for 2 qubits, there are 4 possibilities, which is 2 to the power n. In this case, n is equal to 2. And the operator is supposed to be always unitary, which acts on the given state, as has been shown here. So, we have basically explored the entire process by using the quantum circuit model in most of the cases throughout the discussion in this course, where, for example, we have shown circuits which are lines which are drawn with the operations in the path, and finally we have used measurement as the final result. So, whenever we looked at the inputs, we had the inputs provided, and then we had certain operations For example, in this case there is a 1 qubit operation of a poly X, and then after the 2 qubits are in to the C0 gate, which is the 2 qubit operation, the C0 gate operates and we can have the measurement which gives rise to whatever the process has happened. So, here is the principle of applying how the state goes. So, we have the particular state coming in, it has been put into this 1 qubit operation which switches it to 1, the other unit state as 0 continues. After going through the C0, because the control is a 1, it does its NOT operation. So, it switches the last 2 bits and that can be measured as the final result. So, here is another way of looking at operations on 1 qubit. Quantum NOT gate, for instance, it switches the values of the operations. So, 0 goes to 1, 1 goes to 0, and NOT operation therefore is just a matrix which looks like this. The Hadamard gate, as I mentioned before, essentially creates an equal superposition of the 2 states, and so here is an operation of the Hadamard which is shown here in terms of the matrices. So, we have these equivalent approaches either through vectors or through matrices which go through these processes. Here is another representation of the control NOT operation, where we have used the matrices and the gates vectors in this operation procedure, and as can be seen, this can be represented in many possible ways, and these are the ways that we have discussed in the class as we have gone through. So, here is another example where instead of the 2 pure states coming, we have one state 0 and the other one is a Hadamard state which comes in, and as we go through the operations, how they go and change, it depends. And so, in this particular case, for example, it is a 50-50 mixture of either getting a 0 or a 1. So, the states can be of 2 kinds, where one case where they can be separated and can be written as a tensor products, as is been shown here. Those are called superposition states. However, the other kinds of states where the states cannot be written as tensor products, then those are known as entangled states, as we show it here. So, these states are entangled states, and in case of entangled states, our results are always going to be probabilistic. So, the interesting consequences as a result of this quantum concept is the principle of reversibility, because quantum mechanics is reversible, dynamics are unitary, quantum computations are reversible. The other is the quantum superordinacy, where all classical quantum computers can be performed by a quantum computer. However, one very important thing is there is no cloning possible. It is impossible to exactly copy an unknown quantum state. One of the important things to realize, however, that although quantum superordinacy exists, it is not true that every principle of a classical computer will be more efficient when we go into the quantum computer domain. It might take more steps because of the requirements of the reversibility of the quantum computing process. However, at the end of the day, we all know reversible computers are going to be more efficient, at least energy wise. So, it has its advantages. So, we may ask, what is a quantum computer good for? This is one of the things which we have looked into. Many practical problems require too much time if we attempt to solve them by usual computers. For example, it takes more than the age of the universe to factor a 1000-digit number into primes, because this is an exponential problem. The increase of processor speed slowed down because of limitations of existing technologies. This is one of the facts which has happened. Theoretically, quantum computers can provide truly parallel computations and operate with huge data sets. So, these are the major aspects of quantum computing advantage, why there is a huge research towards quantum computation. So, with this we would like to actually end this first lecture, where we basically bring out the essence of why we were studying quantum computation and its implementation. In the next lecture, we will go into some more details of the very basics that we introduced here in terms of where this entire idea of quantum computers started, how we dealt with it, and how we have benefited from learning more and more about the aspects of quantum developments over these years, and how we have managed to go to a point where we can do implementations. So, from the next lecture on, we look more into these kinds of aspects that we have already discussed in this course. Thank you.